As the #1 selling walk-in tub in North America, SafeStep walk-in tubs are built to maximize your safety and comfort. Each tub comes standard with a dual hydrotherapy system, so you can enjoy the luxuries of bathing comfortably at home. Soothing jets increase mobility and ease pain, while the rainfall shower head refreshes you from head to toe. Visit SafeStepTub.com today to request your free quote and ask about our special offers.
This is SpaceTime, Series 28, Episode 33, for broadcast on the 17th of March 2025. Coming up on SpaceTime, the world's oldest meteor impact crater discovered in Western Australia, more potential locations for water ice on the Moon, and the super-secret X37B space shuttle returns to Earth following its latest mission. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have uncovered what is now the world's oldest known meteor impact crater in Western Australia. Remnants of the ancient 3.5 billion-year-old structure were discovered in the North Pole Dome region of the Pilbara in the state's north. The previous oldest known impact crater, also in Western Australia, was dated at 2.2 billion years. The new discovery, reported in the journal Nature Communications, could significantly redefine science's understanding of the origins of life and how the planet was formed and evolved. One of the study's authors, Tim Johnson from Curtin University, says the structure challenges previous assumptions about Earth's ancient history. Johnson and colleagues discovered the crater thanks to shatter cones, distinctive rock formations that only form under the intense pressure of a meteor strike. The shatter cones at the site, about 40 kilometres west of Marble Bar, were formed when a meteor slammed into the area at more than 36,000 kilometres per hour. Johnson says this impact would have been a major planetary event, resulting in a crater more than 100 kilometres across, which would have sent ejected debris high into the atmosphere, eventually raining back down across the entire planet. He says the face of the Moon is proof that large impacts were common in the early history of the solar system. But until now, the absence of any truly ancient impact craters on Earth has meant they're largely ignored by geologists. Johnson says this study provides a crucial piece of the puzzle of Earth's impact history and suggested there could be many more ancient craters yet to be discovered. Uncovering this impact structure and finding more from the same period could also help explain how life began on Earth. That's because impact craters generate environments friendly to microbial life, such as hot water pools full of mineral nutrients. Johnson says it also radically redefines science's understanding of crust formation. You see, the tremendous amount of energy from this impact could have played a major role in shaping the Earth's early crust. It does this by pushing one part of the crust under another, or by forcing magma to rise from deep within the Earth's mantle up towards the surface. It may even have contributed to the formation of cratons, large ancient geologic structures stretching deep down into the planet that may well be the foundations of today's continents.
So in 2022, we published a paper in Nature suggesting that the Pilbara craton ultimately may have formed above one of these giant impacts of the type that we see on the surface of the Moon, those dark lunar moria, the Imbrium crater. You know, there was very big impacts that hit the Moon. There was very big impacts that hit the Earth. And we believed, as I say, that the Pilbara craton could have been a consequence of these. And we used, at that time, we found some evidence based on the chemical composition of these tiny sand-sized grains of the mineral zircon. So zircon is very, very robust, chemically and physically robust. It also contains lots of radioactive uranium, which decays over time for lead. So we can date it and its host rocks very, very accurately. And we can also measure various trace elements and isotopes of oxygen and hafnium and other sorts of things in these zircon grains to say something about how they might have formed and the processes. Now, that is all a bit esoteric and it's all sort of microscopic or nanoscale science. So it's very difficult to put anybody to get their heads around, really. And I don't think very many, if any, people really believed that paper. So we thought we would go up to the Pilbara and try and look for some more macroscopic evidence, if you like. Could we find the crater or the crater floor? And we simply started our search right in the middle of the exposure of the most ancient rocks. So part of the Pilbara Craton, the most ancient core of it, is called the East Pilbara Terrane, and that is a curiously round set of exposures of rocks about 200 kilometres across, and in the middle of that is a structure called the North Pole Dome. So we headed there, and in particular to find this unusual layer called the Antarctic Creek Member. We were looking for that because that layer, people had formerly found spherules in it. So spherules are quite simply the frozen droplets of melt that forms as a direct effect of the heat of the impact, but they can also form as the result of volcanic eruptions. But at least this layer had some evidence for a distal impact. So we thought we would start there, and we parked our four-wheel drives just off a dusty track heading south from the main road where we thought these rocks might appear. Three of us got out and had a wander around, and we agreed to meet back at the vehicles an hour or so later. And we found, when we did meet back, we thought we'd all found the same thing, which is this feature called shatter cones in the rock. And shatter cones are the only unequivocal evidence that you can see with the naked eye for a direct meteorite impact crater. So shatter cones are known almost exclusively from what are called the central uplift of big craters. So much like when you drop into water, that drop hits the surface and then you have a rebound, the drop comes back up. That's exactly what happens with big craters. So the impactor hits, and then the center, where you've had the maximum impact force, rebounds, and you get something called a central uplift. And that's what we believe this whole big 20 or 30 kilometre wide dome in the middle of the East Pilbara is. And we found the evidence supporting that, which was extremely lucky, but very nice.
The zircons then gave you the date for that.
Yes, so this layer, Antarctic Creek Member it's called, it's a very unusual, very complex layer, a whole mishmash of lots of different things, including broken up bits of basalt and cherts and these spherular layers. And it's sitting in between a few kilometres of basalt underneath it and a few kilometres of basalt above it. These shatter cones are developed right the way throughout this 20 metre or so thick layer called the Antarctic Creek Member. But immediately above them are these beautiful pillow lavas, so like giant toothpaste sort of squirted out, which tell us that they were erupted underwater. But there is no sign of shock at all in those rocks above. And we traced them up for several tens of metres to try and look for shatter cones above where we found them and couldn't find any. The Antarctic Creek Member is also overlain by these really complex carbonate breccias that penetrate into it as dikes and big fractures. So what we think we're looking at is the surface of the crater. We're actually standing on the crater floors in this huge structure, which is the central uplift of the crater. So because we didn't find any shatter cones above, we think the stratigraphic age of that layer, the Antarctic Creek Member, gives you the age of the impact. And fortunately, the geochronologists of the Geological Society of Western Australia had already dated the rocks, and there is a layer of felsic volcanic rocks below the shatter cone bearing horizon, which has been dated by uranium-lead zircon to be 3.47 billion years old. And the basalts above, there is a layer of felsic volcanics in those as well, which has also been dated at 3.47 billion years old. So that provides us with a stratigraphic age of 3.47 for the shatter cone bearing horizon. So we knew we had our age and we had our oldest impact crater.
This discovery is really exciting because we know Earth was formed as a result of meteor and asteroid impacts. It's called accretion. There was a big one about 4.5 billion years ago, which we call Theia.
The moon.
Yes. So we know this happens, but there's also a thing with the Earth called plate tectonics, and also we have erosion and things like this. So the early Earth history is something we know very little about. This ancient impact must be telling us a lot about the history of our planet.
Absolutely, yes. Yes. I mean, we've argued, it's 2018 really where we first got into this, that large impacts were absolutely fundamental to Earth's early evolution. As we can see, they were on all the other silicate bodies in the inner solar system that we can see, be they planets, moons or asteroids. As you say, plate tectonics is an incredibly efficient way of recycling the surface, the rigid surface of the Earth, the lithosphere and the crust, back into the convecting mantle. So most of the evidence is destroyed, particularly given that most of the planet would have been oceanic and most of those impacts would have been into the ocean and they've subsequently disappeared. But we do have areas of really, really, truly ancient continental crust, these so-called cratons that occur in the middle of all of the continents. And they started forming right at the tail end of what we know would have been an intense bombardment from the formation of the solar system 4.5 billion years ago, right up to 3.5 billion years ago. So we should be able to find evidence of these impacts, and we think we do, and we think they would have been fundamental to the processes operating then, including how those cratons might originally have come to be, but also how, for example, the earliest mineral systems, the earliest hydrothermal mineralization systems formed, and perhaps even creating the ecological niches from which life eventually took a foothold and emerged to become us.
The cratons themselves, they're fascinating because they've given a place like Western Australia, where you are, its mineral wealth. It's made it one of the richest places on Earth, quite literally.
Exactly. So many of the mineral deposits, things like gold and nickel and lithium even, are found predominantly in these Archean cratons and at their margins. And we don't think that is a coincidence. So yes, incredibly important processes and incredibly important consequences for humankind. I mean, we argue that large impacts created the land masses on which all humankind walks and the life from which we evolve. So they couldn't be more fundamental in our view.
The link between the cratons and meteor impact side is quite fascinating. What's the idea? That the asteroid slammed into the Earth and it melted everything underneath, and that went all the way deep into the deep mantle, because some of these cratons can go close to the core mantle boundary. That melted material just upwelled because of the lack of pressure, and so it was able to upwell towards the surface, towards the crust.
Absolutely. That's the key point, this decompression. The Earth is a layered structure, and we have this rigid lithosphere, crust, which is sitting on top of the convecting mantle underneath. And the convecting mantle is primed to melt.
Think of it like slow-moving molasses or honey.
Yes, you can also think of it as a bit like a champagne bottle, if you like. So the only thing that's stopping the molasses, the convecting mantle, from melting is the fact that it's got a lid on it, this lithosphere. Okay, so that's like the cork in the champagne bottle. As soon as you remove that lithosphere, or you remove the cork, everything goes mad and your champagne starts squirting out the top. It's exactly the same for the mantle. If you remove the lithosphere with a big impact, then the underlying mantle will melt profusely and produce huge volumes of basalt. So you'll get something like an oceanic plateau, so something like Ontong Java or even Hawaii, those sorts of things. But because Earth had still retained its water, it still had a hydrosphere, and that hydrosphere is still around, you then offer yourself the possibility of reprocessing that thick basaltic pile of rocks into more evolved continental rocks, granites, if you like. So the pale-coloured rocks. And once you've formed those pale-coloured rocks, they're really stable because they're much less dense than the basalt, and they basically float and stay around for billions of years, as we know they have. And one of the fundamental things about cratons, one of the fundamental observations that anybody can make when looking on Google Earth or geological maps, is that they are uncommonly round, and you need to provide a decent explanation as to why that would be, because it's important. I think geologists have perhaps forgotten what we have traditionally been good at, which is making straightforward observations, mapping things and recognizing patterns, and then trying to interpret those patterns. That's exactly how we discovered plate tectonics. The patterns of the magnetic reversals on the seabed allow people to interpret those, that they were sites of creation of new crust.
That's how geology came about in the first place. An observation was made of rocks on a cliff, and they noticed that it was folded over.
Exactly. And
it would have taken time for that folding to take place.
Of course. Of course, and it's those fundamental observations that people interpret. And of course, way back in the 17th and 18th century, we didn't have any machinery to measure isotopes or trace elements or anything like that. It really was what you can see with your eyes and map out, try and make sense of that. But just fundamental observations such as cratons. If you look at maps of the Pilbara craton or even one of the oldest cratons, the Slave craton, it's just uncommonly round, a circular feature, and then that's a very hard thing to do with plate tectonics. Plate tectonics features like spreading ridges or continental arcs like Japan and Indonesia, they're all these big long linear features. That's exactly what you would expect if you have rigid plates jostling against each other, and where they meet, that's where all the action is happening. But you wouldn't expect plate tectonics to produce anything like a circular structure. You would expect that to result from either impacts or these mantle plumes that is the other sort of widely held.
This is the hotspots like Hawaii and Iceland.
Precisely, yes. So in the earlier, the Earth certainly would have been hotter, and you might expect mantle plumes to have been even more vigorously active, but it just doesn't make sense when you compare the likelihood that the impacts that could have given rise to the same thing.
That's Professor Tim Johnson from Curtin University. And this is SpaceTime. Still to come, a new study suggests water ice may be present just a few centimetres below the lunar surface over a far wider area of the moon's polar regions than previously thought. And the United States' secret X37B space shuttle returns to Earth following its latest classified mission. All that and more still to come on SpaceTime. A new study suggests that water ice may be present just a few centimetres below the lunar surface over a far greater area of the moon's polar regions than previously thought. The findings, reported in the journal Communications, Earth and Environment, are based on observations by the Indian Chandrayaan-3 mission in 2023. It showed that the moon's surface is covered by large yet highly localised variations in surface temperatures. It's an important factor because future long-term exploration and habitation of the moon will depend on the availability of ice to provide water. So far, measurements have shown the presence of water ice in cold sinks. These are the dark, permanently shadowed floors of deep polar craters that never experience any sunlight. The only previous direct measurements of lunar surface temperatures were taken way back in the 1970s by the Apollo missions. However, those missions all landed near the equator, where terrain slopes had little effect on temperature. The sites were several thousand kilometres from the proposed southern polar landing sites now being selected for the future Artemis manned missions. The study's lead author, Dugra Prasad from India's Physical Research Laboratory, analysed temperature readings taken on the lunar surface and down to a depth of 10 centimetres by a temperature probe experiment aboard the Chandrayaan-3 Vikram lander, which touched down right at the edge of the lunar south pole. Prasad and colleagues found that temperatures at the landing site, a sun-facing slope angled at about 6 degrees, peaked at around 355 Kelvin, that's 82 degrees Celsius, and dropped to 105 Kelvin, that's minus 168 degrees Celsius, during the lunar night. However, a lower peak temperature of 332 Kelvin or 59 degrees Celsius was measured on a flat region just a metre away. The authors then used this collected data to derive a model of how slope angle affects surface temperatures on the moon, especially at higher lunar latitudes similar to the landing site. The model indicated that for slopes facing away from the sun and towards the nearest pole, a slope with an angle greater than 14 degrees may well be cool enough for ice to accumulate close to the surface. And this is similar to conditions at the lunar poles, including those at the proposed landing sites for Artemis. The authors therefore suggest that areas on the moon where the ice can form may be far more numerous and easier to access than previously thought. This is SpaceTime. Still to come, America's super-secret X37B space shuttle returns to Earth following its latest mission, and later in the science report, we may finally be a step closer to a once-a-year injection which could help prevent HIV infection. All that and more coming up on SpaceTime. The The United States Space Force's highly secretive X37B space shuttle has returned to Earth following a classified 434-day orbital mission. It was the 7th mission for the program, which uses 2 of the winged space planes to undertake specialist orbital testing and reconnaissance operations. The landing at the Vandenberg Space Force Base in California took place appropriately under the cover of darkness in the middle of the night, and the touchdown wasn't publicly announced until several hours after its pre-dawn return. The mission had launched aboard a SpaceX Falcon Heavy rocket from NASA's Kennedy Space Center way back in December 2023. While few details were released by Space Force mission managers, they did say the flight successfully demonstrated the vehicle's ability to change orbits by using aerobraking, that is atmospheric drag, to slow down, in the process saving valuable fuel. And that's an important development, because one of the big advantages of the X37B is its ability to easily change orbits, making it difficult for the enemy to keep track of. Following its deployment from the Falcon into a highly elliptical orbit, the reusable spaceplane conducted what Space Force describes as space domain awareness technology experiments that aim to improve America's knowledge of the space environment. Now, that word salad suggests that one of its functions is close proximity inspector missions, studying, imaging, and maybe even attaching spy equipment onto enemy satellites. First launched back in 2010, the Boeing-made autonomous spacecraft are based on a prototype originally developed to be transported into space in the payload bay of NASA's Space Shuttle fleet and then deployed on missions lasting well over 900 days. And the previous X-37B mission, OTV-6, lasted 908 days in orbit. Genuine proof of concept. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Early-stage trials suggesting that a once-a-year injection to prevent HIV may now be a step closer to fruition. HIV is the human immunodeficiency virus, which causes AIDS. The findings, reported in the Lancet Medical Journal, found that one injection of the drug lenacapavir into the muscle resulted in the compound remaining detectable in the blood for at least 56 weeks. At the 1-year mark, the study found the drug was safe and that blood levels of the drug were still higher than those recorded in previous studies where the drug was shown to block HIV transmission. However, as a Phase 1 study, the trial didn't actually measure the drug's effectiveness at preventing HIV infection, and so further clinical trials will be needed, including with participants from more diverse population sets. Scientists say the record-breaking high sea temperatures of 2023 and 24 were strange, but not totally unexpected when looking at climate models. A report in the journal Nature's found that global sea surface temperatures reached record highs, breaking the previous records by around 0.25 degrees Celsius. The sudden increase raised concerns that global warming might be accelerating faster than models had predicted. However, looking at observation-based statistical models, the authors found the jump was considered to be a 1 in 512-year event relative to current warming trends. This means that while such an anomaly would have been practically impossible without current global warming trends, the event's not entirely unexpected. Paleontologists have discovered rare dinosaur footprints hiding in plain sight at a central Queensland high school. A report in the journal Historical Biology identified 66 fossilised footprints on a boulder at the school, representing one of the highest concentrations of dinosaur footprints per square metre ever documented in Australia. The footprints are from 47 individual dinosaurs which passed across a patch of wet clay while walking along or crossing a waterway during the early Jurassic some 200 million years ago. The three-toed footprints belong to the ichneospecies species Amorphoscampus, a small bipedal herbivorous dinosaur between 15 and 50 centimetres in length, with long legs, a chunky body, short arms, and a small head and beak. The boulder containing the footprints was uncovered some 20 years ago at a local mine and then given to the local high school. And it wasn't alone. A second rock, also containing dinosaur footprints from 2 different species, was found decorating the mine's car park entrance, while a third, much smaller dinosaur footprint-covered rock had been encased in resin and was being used in the office as a bookend. that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies. Or by becoming a SpaceTime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.